We have a great group of panelists with us today. Before we get to that, just a little bit of background. Solar is something we've been integrating in the utility industry for decades now. It becomes a very interesting topic when you start looking at the integration technologies that are available, considering there's at least 18 different methodologies that I've run across myself. So today we want to look a little bit about how power electronics can supplement or supplant those technologies, how the business dynamics are kind of forming in the U.S. market specifically, and maybe a little bit as well as internationally. So with that, just want to let our panelists introduce themselves and provide a name, company, a little bit about yourselves, as well as what do you see as the most important driver in the next 5 years for the deployment of utility power electronics?
So I'm Naimish Patel with Gridco Systems. Gridco sells power regulation infrastructure at utility scale to enable utilities to, for example, increase the hosting capacity of their feeder systems to PV, to render higher levels of energy efficiency through things like CVR and advanced volt-bar optimization, and also to manage the capacity on their feeders in the presence of increasing disparity between peak loads and average loads.
My name is Chad Eckhardt, and I'm President and CEO of GridBridge. GridBridge is a developer enabler of advanced power delivery systems, and specifically within the electric utility, focused on the distribution grid. We're focused specifically on utilizing power electronics-based technology, embedded software, and distributed software to offer the utilities a host of benefits. And we're teamed with a couple of the nation's largest research centers in Research Triangle Park, North Carolina, where we're actively working in partnership with utilities to bring out new products or new devices that help them solve major problems.
Deepak, Divan. I'm President and CTO and co-founder for Varentec. We're a company about 3 years old, located in San Jose, California. I think what we've kind of seen is that the grid edge, which is aptly the name of this conference, there's a lot of problems at the grid edge in terms of volatility, in terms of precision of control, and in terms of dynamic response. And it's our belief that solutions that are required are really distributed, decentralized solutions. We've now been offering these solutions for several years, and have been working with utility partners to kind of prove the technologies out, and are now looking to to scale those solutions up. So we're happy to chat about that.
Good afternoon. I'm Jason Handley. I'm with Duke Energy. I'm in our emerging technology office. I'm the director of operations and projects. Low voltage power electronics have a wealth of good uses for us. We have already started testing devices on our system to try and figure out exactly what the limits of these are. As far as what we really need for them, what really needs to happen is we need for pricing models to become a little bit more advantageous for us to get more penetration in to our distribution system.
Okay. Just want to start off and also give a special thanks to Jason, because we had one of our panelists actually had a personal matter that kept him from getting here, and Jason was nice enough to step in. And with that, I'm going to throw him directly into the fire and start off with, when you're looking at distributed generation, specifically solar, how is it actually affecting your grid right now? Obviously, the amount of information collected is increasing, but what effects are you seeing today within Duke or within your experience?
Sure, Ben. The effects of solar on especially the distribution system are growing. I think everyone knows here the issues with intermittency of renewables, especially around solar. And we are seeing that in our service territories today. Surprisingly, mostly in our North Carolina service territory, which is the 5th largest growing solar territory in the United States right now. So we are starting to have to actually ask people to stop putting solar out on some of our feeders because of the volatility it's causing until we can get better devices, better technology out to be able to handle it in a much more synchronized way.
Okay. I don't know.
Yeah, I'd love to kind of add to that. I mean, we see a problem emerging, and one that's very difficult for utilities to handle with the conventional means that they have. I I mean, typically it's a bit of a planning problem where, you know, if you design it right, then you set the taps on the substation so that you get, under worst case conditions, low voltage. And then, you know, when you have light load and you have solar coming back in, you have high voltage, and, you know, that's a very tough thing to handle, that steady state. And then there's the dynamic problem, you know. So it's been very challenging, I think, for utilities to kind of to tackle it. And on the other hand, that's an emerging problem, okay? And it's not everybody has that. And, you know, how do you start and run a company waiting for a problem to emerge? I think so that's, you know, from an entrepreneur standpoint, you know, that's a bit of a challenge. I mean, so you have to go after those things that have a need today and position to make sure that as these problems are emerging, you're there to provide a solution.
I think certain utilities would actually disagree with you there, Deepak. So certain utilities are seeing these problems now. And today, their only solution to address these is to actually invest in more copper or aluminum, basically reconductor, or install larger transformers in an attempt to mitigate the voltage rise that occurs as a result of high penetration PV. So whether you're talking about utilities in California, whether you're talking about utilities in Germany, or Ontario, or Hawaii for that matter, or Australia, or Japan, these problems are occurring now. And the question then becomes, what's the most cost-effective way, systemically, to deal with these issues? And can you actually come up with a solution that's lower upfront capital cost than reconductoring or larger transformers? That becomes the fundamental problem to solve. And one has to take a systemic view to understand what's needed from a technological perspective to address that. And it becomes pretty obvious what you need to do, is you need devices that can buck voltage or reduce voltage in the presence of PV, and do so, as Deepak mentioned, in a dynamic fashion, because electromechanical equipment has this unfortunate trade-off involved where the more that they actuate, the lower their lifetime. And so that's fundamentally why power electronics provides value in these situations, because of the dynamic aspect of PV integration.
If I add just a little bit to that, voltage management is one component, but then we also need to look at the VAR component, or power factor correction. And if we look at solar panels, the way they're designed to offer real power. Well, the sufferer in that process is the distribution network. So the distribution network then, as a result of seeing the real power onto the grid, needs to react with reactive power. And so the distribution network suffers in that process, and there needs to be a VAR compensation component as well. And that's why we're starting to talk about some of these power electronics. And these are issues that are certainly emerging. They're difficult to measure, but they exist inside the utility grid. Another one that I think we can add is harmonics, right? Harmonics are the dirty secret. They exist, but no one really wants to talk about them. Specifically in the inverter technology, when you look at putting inverters, say, of the same manufacturer on a specific phase, and you standardize on those inverters, you're going to see a host of fifth harmonics coming onto the grid. And so those are problematic because they cause heating, lower efficiency.
And so all of those answers just about were good enough to get about 6 questions down the line. So one thing I do want to bring out, you know, we had our Grid Edge Executive Council meeting yesterday. And one of the things that was mentioned as one of the biggest technological barriers for PV integration, which actually the technological barriers are much, according to everybody's opinions, much lower than expected. Partially because they're seeing a lot of power electronic solutions, battery solutions, et cetera, come online. But one of the things that mentioned was grid planning, long-term planning to understand how much is going to be on your lines. And Jason, as you mentioned, you guys have the benefit of saying, you know, we can close the tap off until we know what to do next.
Today.
And that changes. In Hawaii, right. That's gone away. I mean, they had that ability up until about a month ago, where they said you have to run dynamic simulations. You have to understand what's going on. So when we look at how things are going, in that grid planning aspect, and in that even that immediate step aspect, how do you go about increasing carrying capacity for solar, and just how are you guys looking at that right now, or how are you expecting the market to move?
Well, we're actually going to have to pretty much look at our entire planning model again, because traditionally all of our planning tools are based on one-way generation, one-way load flow. So the advent of distributed generation, whether it be PV, wind, any type of renewable, is causing us to rethink exactly how we go about our planning process. what we're finding out is we're not necessarily equipped with the tools at this point to be able to go in and fully look at doing a two-way power flow. There's tools that are now available like OpenDSS that we can use, but some of the traditional means like SIME have not necessarily come as quickly as we wanted to with them being able to do these types of functions. So, and it's also really starting to retrain the power engineer of today. I know this has not necessarily a lot to do with renewables, but I'm going to say it since I have a minute. The power engineer of today is basically where the lineman was 15 years ago. We put technology in the lineman's truck, asked them to change, asked them to start leaving their paper tickets behind and starting using a computer. The power engineer of today has got to understand that they no longer can only worry about the electrical side. They need to worry about the IT and the telecom also. And so I think with the advent of the power electronics and how that comes about with how we're going to have to feed everything back in through a system, looking at not only load flows and how we're doing load allocations down feeder lines is really going to be a problem that we have to start addressing right now.
So I think the software angle is a good place to start. I know I've talked to each of you individually and heard exactly that comment about the planning tools not being there. You know, the experiences you guys have and kind of what you're seeing come down the pike with vendors that you may be partnering with or internal solutions. What's needed and how far out is it before we actually get some planning tools that are effective at actually understanding these problems?
Well, I think let's first cast the problem in. There's two actual aspects to the planning tools. You know, there's one, both of which Jason mentioned, but they're important to delineate. So the first is sort of what I call the static aspect of planning, which is the fundamental problem is to know where you're going to have a challenge, whether in voltage or VARs or whatever it may be, and then locate a device, an economically feasible device, at the location. And then there's the second part, which I would say is more about validation of the solutions that you're going to put out there, which does involve a transient analysis, because there you want to know that the black box model of the device that you're considering putting out has the intrinsic capacity and functions to be able to adapt in real time to address the time variations of PV. The first one is a lot simpler than the second one, let's be clear about that. And moreover can be derived to first order from existing tools, albeit with some modifications. And I think actually that's probably the one that after you've done validation, you actually want to focus most of your effort on, because that is, at the end of the day, is the core operational issue that utilities are going to grapple with is where do I go and put these systems to address the problems I either have now or I anticipate having as a result of my forecast for PV. But the static one is more easily addressable, I would say, than the dynamic one, and that's a good thing, I think.
And I think I generally agree with you, Naimish, because we see the same issue. There's a static issue where people have to kind of know where placement of devices needs to happen and where the voltages are going to be what they are. There is a stochastic element to that as well, so that needs to be modeled, and there's a little dynamic element to that. And the other thing we're finding is that the grid edge itself, the transformer, okay, the drops across the transformer are substantial, okay, and are dynamic. And are really coming back to limit some of the things that the utilities are trying to do in terms of voltage regulation, voltage maintenance, and things like that, right? So, that is kind of also letting you know where to place devices and what the devices need to do, and whether the devices are kind of just repairing a voltage downstream of them, or are they repairing the entire feeder voltage so that, so these are all important issues that I think everyone is trying to tackle in a completely different manner, and I think a lot of differentiation out there in terms of solutions.
So when we look at, the decision that right now a lot of these things, especially on the transient side, are not there. In the meantime, and I want to start with Chad on this. What type of prototypical feeders is there a step in which you can say, I'm a utility, I expect a lot of solar to come online. What are my danger feeders? Are there tricks of the trade that you've come across? We know that if it's a rural feeder that's 30 miles long, that's the one we need to concentrate on first.
So, the answer is always it depends, right? Every utility is different, and the approach at each utility is different. Jason can speak towards some experience at Duke Energy and how problematic feeders are identified and looked at for utilization of certain technology. I can say that what we're talking about with power electronics and putting power electronics on the grid, there's a host of available benefits that can be offered. And so if we're just looking to solve one particular problem, such as overvoltage or undervoltage, right, then that feeder's identified one way. If we're looking at a potential feeder in the future that's going to have a high concentration of photovoltaic or is going to have some sort of clustering effect based on models social models that the utilities looked at, then that's another way to approach and highlight a particular feeder for certain technology.
I don't know if Jason, you want to add on to that?
Chad said it pretty well. I mean, it really comes down to the impedance of the line. I mean, looking at exactly, what your wire size is. If you have a pretty stiff backbone, it's not going to affect you as much as if you do have a really rural feeder, and all of a sudden now you've gotten, a megawatt of solar at the end of the line. I mean, those are the kind of things that really cause the utility operations folks a lot of heartache today.
So I know earlier, especially on I believe the Solar Utility Nexus panel, we talked a little bit about how different technologies are actually interrelating and how much capability can be derived from the inverter. We had the 6 solutions popped up, and obviously we have a very weighted panel towards number 6, so obviously anybody in the audience feel free to take that with a grain of salt. But when we look at solutions like smart inverters versus grid power electronics versus battery storage, on the scales of what's required at different penetration levels, is there any guidance you guys have run into, any general rules of thumb on what should be done first, as it's something that's completely geographically dependent? Kind of how's Duke looked at it? How have you guys looked at this?
Well, go ahead.
Well, so the good thing about this is this is all calculatable. I mean, it comes down to what Jason already mentioned. If you know the X and the R, the complex impedance of the secondary, you can actually calculate which solution is most cost effective. So, and of course, it is a function of the penetration level. So at relatively low penetration levels, where you only need to be able to move the voltage on the secondary by 1 or 2%, then VARs, whether as a result of a smart inverter or another utility-owned device, can actually reasonably well solve that. If you've got a problem beyond that, where the penetration levels are giving rise to situations where you need to compensate for multi-volt deltas or multi-volt changes on the secondary, then you need a lot of reactive power, unless you've got a particularly high X on your feeder. And so general rules of thumb can be derived. For example, if you have underground distribution, which happens to be the case in California where there's a lot of high PV penetration, and it certainly is the case in Germany, for example, then the line's contribution to X is comparatively small. So you have to rely then on the transformer for any delta V that you're going to get across it. And the larger the transformer, the less the delta V you're going to get. So these are all very easily modelable and in isolation, I might add, if you're just trying to solve a secondary problem. But at the end of the day, I think we all agree here that every situation is different. But I will also say at high penetrations, you do need something more than reactive power, because either you're going to use a lot of reactive power, which implies lots of power electronics, or you're not going to be able to solve the problem.
And so
I want to let Deepak go, just because
Go
I
ahead.
have a feeling he's the one that wants to talk the most
I
right now.
fundamentally disagree with that, of course, but
and I'm in the middle.
yeah.
Let's have the debate.
I think physics is physics, right? It has to operate the way it does. And I think I think your general comment is probably true. I think what we have found is that it's the distribution transformer that really adds a lot of X to the system. Okay, and if you're trying to regulate the voltage on a secondary side, we can get, if you need 200 kVARs of reactive support to give you a 1 volt difference on the primary side, on the secondary side, we might need 3 kVARs to give you the same effect. So there's a very substantial difference that we have found based on data coming from feeders after feeder after feeder. I mean, so this is not just hypothetical analysis, which very clearly shows that you can have that impact. The second thing that we really fundamentally believe is that, it's about supporting the grid and making the voltages at individual customer points, good at the same time, right? If I have a series device that kind of regulates the voltage on the secondary side, I always make the voltage on the primary side worse. Okay, because power balance has to be followed across that device. A lot of the solar panels are constant P devices, which again creates that same issue. So our belief is that what you need to do is you need to have judiciously deployed VARs that support the secondary side, the local voltage as well. A lot of the reflected VARs flow up on the primary side and support the primary side well. Okay, and then in locations, 1 or 2 locations, you may have to go put series correction. So that's a slightly different way of coming at the same problem. And we've now, we've got field data, and we've got extensive modeling data that's coming out of it that shows that you're able to, with VARs, and taps and LTCs that kind of operate the right way, you're able to actually provide very, very good dynamic and static performance. So that's our belief.
Well, but in the context, just to clarify, in the context of PV, you need to buck voltage. You don't solve anything if you're going to increase voltage in the context of PV, because let's go back to what the problem is. The problem is that there's an ANSI rule, or Rule 2 for equivalent in California, that states you must be on the secondary at the point of coupling, not on the primary, at the point of coupling where the customer connects, within the ANSI range. So the only reason utilities are going to do anything about PV integration from the perspective of voltage is if they're getting violations or if they forecast violations. So first and foremost, they've got to be able to reduce voltage. Second, they need to be able to reduce it by an amount enough to ensure that they're within the ANSI range, even if they're seeing further growth of PV. Generally speaking, from what we've seen, that's more than a volt. So if you need more than a volt, VARs isn't going to give you the solution. It's just not going to be able to move it enough.
And I think we can fundamentally
make
agree
one
to disagree.
comment. I will let this continue. All right, we'll point out, part of our presentation will be understandable to people without PhDs. If you can't tell, there's a few PhDs on these guys' teams. So let's continue for a couple more minutes, because it is an interesting problem. For those of you, it is live streamed. It will be available later on for anybody that has technical guys in their team that they want to review this. So continue.
And I suggest, you should come and chat with your team as well as our team, and we're happy to share data and the analysis.
Jason, I think you want to weigh in.
Yeah, I really believe that there's not one solution, as always. So Chad said it depends, and the good lawyer always says it depends. But it's going to be a combination of low voltage power electronics. It's going to be a combination of smart inverters. It's going to be a combination of batteries. There is not one tool out there that I can solve all of my problems with today for PV. Now, I do have to say that full disclosure here, I have 2 pilots going on with 2 of the companies up here, and I'm about to start a 3rd with the other guy. It's not like I'm not familiar, but one of the use cases that we did look at was for a customer. Wasn't solar. It was because we have a 2 megawatt solar facility near a bunch of residential customers. So we are using VARs in that case as a use case to mitigate the intermittency. So it's not necessarily that we're trying to drive voltage down. We are trying to dampen out any of the intermittency that may be seen for our customers. So we're trying to provide better customer service through that type of thing. So I understand exactly, Naimish, what you're saying. I agree to a point, but I do think the utility has many more use cases to where low voltage power electronics, and I think what I'm saying is I agree with all of you that the future for low voltage power electronics in the utility industry is very bright. I mean, we have an extreme thirst right now to have more of these types of devices that we can test and find out exactly what the capabilities are going to be, because we see the potential right now with just the work we've already done.
I think the only thing that I'd add, just going back to the original question, is as we look at the capabilities of power electronics, the danger is to go down the path and say, all right, we're utilizing smart inverters, or we're utilizing energy storage intelligence, or we're utilizing one of these point-based solutions that solves the scratch. It just solves the problem or the immediate problem, but it's not helping look at the totality of the problem inside of the distribution network. And so the utility is, again, best suited to do that, and there's companies that are best suited to look at, okay, I have a problem on my distribution network and I'm planning 5 to 10 years or even 20 years out. I'm not just looking at how to tie in PV and how to manage through an increased level of penetration. Because if we do that, if we follow down that path and we just use one particular technology to solve that point-based problem, we're going to be here again in another 2 years or 3 years talking about what the next latest, greatest technology is. And so that's insurance for all of us to keep developing technologies, but still keep them open enough to help solve a multitude of problems.
I'm gonna
what
cut
we're
that
seeing.
question off right there. We have similar questions, but less PhD. So we're going to transfer into our slightly less, more business-focused section. So one thing that got brought up in the last actually 2 or 3 comments was different applications. And applications are important when you're looking at it. As said, it's not just voltage control. There's intermittency issues, which power electronics are great for intermittency issues. But there's also some other beneficial things just for the utility in general, because we're not talking about a single actor, which if you have a solar facility, your goal is to sell power. Utilities have a lot more, many more services that they have to provide, and these types of solutions do provide some additional value. So just on the most important top 3, say, just want to let Deepak start off. What are the top 3 value streams that utilities should be looking at for these types of solutions?
I think that's a really important question, because again, I think every utility is different. The answer everywhere is it depends, right? And so when we kind of approach the problem, we approach it at a more fundamental level and said, for grid operations, what are the things that are required that we can provide, services and support for? And I kind of broadly kind of separate them into 3 categories. One is what I call the local problem, which is on the secondary side, and it could be a low voltage issue, it could be dynamic issue, could be a motor start issue, could be anything, any of these things, or could be solar for that matter. So that's one area of problems, and that if you can fix that problem, it then stimulates a whole bunch of applications for the utilities, whether it's CVR, whether it's peak demand management, whether it's improved volt VAR optimization. I mean, any of these things that can be stimulated once you have that kind of technology that is deployed. The other one that is there is really precision of control. So, power electronics gives you dynamics, and it gives you, continuous control capability, which utilities just don't have. I mean, the only continuous VAR control they have resides in generators, which are very far away from the points where the problems are occurring. Okay, and what the power electronics can now give you local control capability, which can then be usefully deployed in terms of precision. And the reason precision is important is because utilities are now being asked to do more with the assets they have. Okay, so they have to squeeze the voltage into narrower bands and be able to squeeze demand out of it, or squeeze energy conservation out of it, or any of those things. So, when we've approached the problem, we said there's a precision issue, there's a dynamic issue, and if you can solve these, then you can solve these at a system level and at the local level simultaneously, and at a cost point that hits Jason's argument, which is this is still too expensive. Then we have a business. So I think that's kind of the approach that we've taken. Is control, is precision, and local, and at a feeder level.
I think I'll add a little bit. I mean, we started 4 years ago in talking with utilities. We started with a list of probably about 15 different capabilities that we could offer as a service. We narrowed that down very quickly to an addressable set of problems, and I can say that list of 15 continues to grow. The combination of power electronics with embedded software at a key location is a very powerful combination, and really will help the utility move into the next phase. I'll end up saying very similar to what Deepak has mentioned, but say it in probably different words. I mean, we bucket things into the integration of DC-based devices, efficiency, right, which is CVR and programs demand management, as well as the reliability and resilience. And so those are the themes that utilities, as we've spoken with hundreds of utilities about where the problems exist and the things that they're concerned about in the next probably 5, 10, 20 years.
I just add one thing. I agree with both. I think just putting a different lens on it. I think what you're hearing is there's long-term strategic value to having power electronics on the grid. I think there's no doubt that that's true. It's important, however, that whatever solution one's bringing to market cost-effectively addresses the problem that's most dire at the utility, because otherwise it's very difficult to be able to make the case for deploying equipment, particularly at scale, if you're relying heavily on future returns as opposed to today's problem. Now, the way we view sort of the value streams that come from or can be derived from power electronics, there's really 3 buckets. First, we generally call it sort of the power delivery assurance, or power quality assurance, and that's the idea that I think Deepak refers to that as the local piece of it, which is to say you want to certainly make sure that you're delivering voltage within the range, the mandated range, but you can also address things like flicker or sag mitigation or harmonic cancellation. because those, in certain cases, do have customer impact, and that actually sometimes gives rise to customer calls and complaints. And so generally the idea of service quality assurance is one bucket of value that can be derived. If we go more fundamentally, though, to what really drives utility investment, at the end of the day, utilities invest in capital for one reason and one reason alone, which is to maintain safe and reliable delivery of power to their end customers. And so if we look at the trends that most utilities are seeing, independent of geography and independent of where there's PV, for example, is that their peak loads are generally increasing at a rate faster than their average loads. Nevertheless, their revenues scale as average loads, and their capacity investments, their capital investments, scale to accommodate their peaks. So there's an increasing discrepancy, almost at every utility, in the capital investments they must make to maintain reliability of the system, and on the other hand, the revenues that they're bringing in as a result of volumetric sales model. And so the second bucket of value that I believe power electronics is going to bring is the ability to manage their capital investments to be more consistent and proportional with their revenues. And that comes down to everything like peak demand curtailment and also some more futuristic things around the idea of moving power around to address capacity constraints.
Ben, the way that I view it is the power electronics are an enabling device for me. It can potentially be the baseboard or the first level of my entire distribution platform. So it's not a device anymore. It's the ability to have processing and memory capability out there. I could potentially add apps onto the device. It's a hardened computer. So it's a platform. Don't think about it as a device, because if you, again, what everyone else has said up here I think has been correct, that you don't want to pigeonhole. The one thing at Duke that we continue to strive to do is we continue to say we no longer can have siloed purpose devices, single purpose devices. Things need to be modular, things need to be multifunction anymore. So far, low voltage power electronics is the most modular piece of equipment that I've seen come out on the grid, because it allows me to start the base of my platform, which is, we call the distributed intelligence platform.
So on that note, I actually am curious, because talking about that right now is mainly a supplement, but how exactly should we be looking, how a utility starting off, how should they be looking at where and how to place these devices cost efficiently within their current infrastructure? Because obviously there's many differences on each feeder. How are you guys interacting your capacitor banks with this, for instance? How are you interacting voltage regulators or existing equipment that can do the bulk of the work, but not necessarily the dynamic or local work?
Sure. Well, we are lucky at Duke to where we have a smart grid test area. And so we basically throw anything that has to do with smart grid in this one 6-feeder area. And that's the other reason we're really big on interoperability. But what we have today is we have devices like capacitors, line regulators, that I call coarse devices. All they do is they do step function change. The low voltage power electronics are that fine control. And so with sub-cycle response times, my customer may not even know that anything has happened. I can pretty much, if they, in the future, I can pretty much guarantee them a voltage. So, you know, it's important to us to be able to provide that kind of service to our customer. So, you know, if a plastic injection manufacturer that makes plastic Coke bottles needs 480, not 479, not 481, potentially with power electronics we can do it.
Yeah, and that's something internationally that has been a bit popular, mostly from the industrial side, buying their own equipment. I know in Korea you've seen some power electronics on the low voltage side pull into semiconductor manufacturers for that exact reason.
And your question really went back to your first question, which was about the feeder of the future. The feeder of the future is going to look completely different than what we have today. We are still struggling with how do you even model it? How do you determine where are the right places? So if I no longer have to put in line regulators, line capacitors, what does my model look like now? These new devices that are coming out, you know, how many do I need? Where do I need them? So again, kind of wrapping this all back up into a couple of questions that you've already asked, is we're still in the very much beginning phases and learning processes of this. So that's the reason we need the tools, and we need to continue the experience with the devices in the field to get more understanding about actually how they're going to operate.
I think one thing I can add, if I could just chime in a little bit to Jason's answer, is when we've touched upon cost effective multiple times, and so cost effective is very important. This is a different technology than maybe we've seen in the past, and in the past we've seen large software overlays going into the substation by and large, into the control center. This is something different. It ties into the control center, right? But it's distributed technology. It's plug-and-play type technology that can be deployed as the utility needs it. We are not going to utilities and saying, please, here's a $10 million type solution that's going to solve all your needs for the next 100 years. What we're saying is, here's pockets of distributed technology that you can deploy very easily to solve problems.
Although that may change too, right? I mean, I think when the solution gets to be, kind of ubiquitous, then it will be deployed more uniformly. I mean, that would be the ideal thing, because, I mean, we see so much of variability on the system that you may need it today here, and tomorrow you may need it there, and the day after tomorrow you may need it there. And now what are you going to do? So, I mean,
Right.
so this is part of, I think, challenge.
But today the use case for us, I mean, we have an unregulated, or I should say a deregulated market in Ohio, and we are required to do volt var control in that market. And so we are limited, as everyone on this panel very well knows, by maybe 5 to 10 transformers per feeder, about how much we can actually take down that voltage for the entire feeder, because we only have these coarse devices like capacitors and like regulators. So the thought is we're going to go put in 10 to 15 of these devices at these low voltage spots and see how much actual bandwidth we can now get to lower the voltage and provide that better quality of service to our customer. And so that has a dollar value for me that I'm going to have to be able to turn around, and that's how I'm going to go through and look at economic evaluation.
Yeah, I mean, that's a couple things I do want to mention, just to give a little bit of context. On the guaranteed voltage side, you actually have seen service quality be a mandated thing in some Scandinavian countries already. So it's a nice hedge for long term. I mean, today I don't think any PUC is even looking at that, but considering AMI has taken off a lot of their time.
We don't need to mention that outside this group.
Everybody who's on the internet, just ignore that.
I just want to mention that I think, we've talked about power electronics. What I want to do is encourage us to kind of go one level higher. And rather than specify the technology and specify what solution it is, let's look at what characteristics are required for support the grid. And whether you do it with sticks and stones or you do it with the latest in gallium nitride devices doesn't really matter to the end customer. Okay, so, and as long as the cost is met, big component of losses, the big component of total cost of ownership is losses. So I mean, all of these things had to kind of be counted together to kind of figure out what the value is being delivered to the utility.
So that just looking at actual deployments of these technologies, when you say getting more out of your CVR, for instance, are we at the point where or I should say, when are we at the point where it actually is something where it makes sense in territories that are promoting CVR, for that matter, like Ohio, or Maryland, for that matter, where it's mandated? Well, the integration over time is mandated. Does it require something like in TVA's region, where you have a G&T that's basically increasing demand charges, and also supporting many of its distributors that they provide power to with some incentives for things like CVR, including direct pay for the energy reduction? Is that required? Or are we there?
CVR is one of the hardest ones, because I mean it starts off with the utility losing revenue, and there has to be some kind of a makeup that is provided by the commissions. And if you don't do that, then you're not going to get it. But I think we're starting to see more acceptance of the fact that there should be an offset for that. That we're seeing more acceptance that this can be an energy efficiency play, can be a demand response play that is utility side. So there's a whole number of different value streams that slowly are starting to be integrated together. And we've talked to probably a dozen commissioners, and at least there's an increasing acceptance that this needs to be dealt with more. The time constants worry me as a startup, but I mean, at least the movement's all there.
Well, I mean, I think, the challenge with any new technology as applied to a relatively mature market is finding where the pain point is the highest and the ability to and desire to invest is the highest. And then as others have noted on the panel, once you start to have more broader penetration, not only do your costs come down, but then you're also able to address a broader set of applications. And so I go back to where do utilities feel pain and what are they already incentivized to spend dollars against? And the one, by far, the one that most utilities are concerned with is reliability. So if you go to any area where there's a reliability challenge, either present or anticipated, that's where you're most likely to be able to address, and on a reasonable timescale, the problem that they're facing. Everything else is secondary. Now, if it comes through mandate, like CVR, that's also a good instigator for spend. But at the very basic level, if you can deliver something to utilities to help them manage unreliability in pockets that they may be seeing, that's the easiest way, at the end of the day, to actually gain entrance.
Just to clarify for people that may not be as familiar, when you were talking about reliability, you're talking about things like ISO level emergency voltage reduction type of things where you have brownouts and whatnot. Or are you talking about other aspects as well?
Well, there's a variety of different things underlying reliability. There's the power quality aspects of it, which are about voltage compliance. There's the systemic aspects of it, which are about peak demand curtailment at times when you need it. And there's other aspects to it that relate to as load has grown, but investments in infrastructure may not necessarily have grown commensurately. How does one most cost effectively deal with maintaining reliability on older circuits? And so, which is fundamentally about capacity management. So there's a variety of different things, but as long as you can link those to the basic requirement of delivering reliable, safe power at the most cost-effective price or cost point, then at least there's a shot of getting utilities to invest. Everything else is tertiary.
It's a preventative maintenance play too, because with having the power electronics out there, it's basically a sensor. And so you can add different functions to that sensor. One of the things that we're looking at and we're doing is partial discharge for our underground cable. So as soon as you start to see signatures for arcing over the insulation, you can start tracking the partial discharge on your cables. I've not had that type of ability to track that in the past. Again, it's a hardened computer that we're putting out there. So there are many different use cases that potentially can come out of this. But from the reliability side, that's one of the things that we're looking at from a preventative maintenance is really looking at partial discharge.
That brings me up to one point that we don't have time to get into, but I wish we could actually get into a lot of the data aspects of this because it gets pretty impressive. Just relatively quickly on the performance metrics side of things, we talked about value streams. At Duke, for instance, how are you guys looking, or how do you expect to look at these solutions and understand, this is going well because of the voltage reduction, or is it things like how you use the data? How are you guys evaluating right now?
Well, when we first started out, we were looking at solid state transformers. So a medium voltage conversion to a low voltage conversion. Well, today what we have is when we looked at the benefit stream, it was about 12 different use case benefits. 8 of them were on the low voltage side. So we said, why can't we just immediately start producing something and putting something in that can have a benefit for our customers now? And that's where the low voltage power electronics, at least on Duke's system, have started to be implemented from. And so those 8 characteristics that we're looking at, or 8 use cases that we're looking at, are being evaluated on a consistent basis because we are getting streaming data from our devices right now. So we're looking at not only are the ways that we're able to quickly respond to voltage fluctuations through intermittency of solar, but the way we're able to respond to demands for lowering voltage for a demand response event. And there's also the additional of being able to throw in VARs when you need to support the voltage. So we have 5 or 6 specific areas that we're looking at. And we haven't even spoke about safety, because one of the other things that this can do is it can identify an open neutral So, these are the kind of power electronic devices that, again, I'm coming out of my chair a little bit because I'm very excited about the potential for this in the future. I really do, and pardon the pun, to me, this is going to be one of the most transformational devices in our industry in the next 100 years. I really do believe that.
Yeah.
I think, performance metrics, are important. We need to take a look at the distribution feeder today, and not to get extremely complex with performance metrics, but we need to look at simplistic things like power quality. How today do we measure power quality at every individual transformer point? We drive a truck out and we put a meter on it. And we set that meter there for a number of days and get a reading back. Hopefully the conditions are favorable to getting that data, and we can do something in the future. These types of capabilities can change that. And so the performance metrics, your question was which specific performance metrics should be in place. I think it's more the knowledge that can be applied to the distribution feeder network by having localized transformer-based type controls and knowledge. And so the ability to pull all that back to the utility is important, but we need to balance that as well, because in conversations with utilities, some of them don't want to be overwhelmed with data. And so we need to manage it wisely. And one of the things that can be done, we've seen a lot of point-based solutions that go on to meters, go on to transformers, but all that data ends up going back to the substation, and it's analysis paralysis in terms of the utility trying to do something with it. And then they look around and say, well, what equipment do I have to solve the problem? And it's still a line regulator, load tap changer, and a capacitor bank. And so the data doesn't really help them out. And so what we have, again, worked with utilities on is you have valuable data, you have a device or power electronics that can make a change locally, and these types of performance metrics are only important if you're not overwhelmed by them.
So we're still at step one.
Yeah, well, one more thing out here, I think. Certainly the metrics are critical for validating the performance of the devices, which is the basis from which all the value is going to flow back to the utility. So it's critical step number one. But I think the challenge we face is that every utility is different. Every utility has got different practices, it's got different constraints, it's got different regulatory environment, everything is different, right? And so to take that basic technology that you validated through metrics now to go forth and build use cases is a huge challenge by itself. And especially for startups who are kind of getting going and trying to focus on this. That tends to be a really major issue that we all have to kind of tackle. So the more we can kind of figure out how to kind of get some kind of harmonization on use cases that you can then interpret different technologies and solutions on, that's going to be helpful for everybody, I think. So.
Yeah, I agree. Rules of thumb have been developed over a long period of time for the design, dimensioning, and operation of distribution feeder systems, and they're good rules of thumb. I actually think that out of this process will come a new set of rules of thumb that deal with not only voltages decreasing along a feeder, but voltages increasing along a feeder, and time varying aspects of those voltages. But I think actually it is possible to render such rules of thumb, perhaps by application, as you suggest. That's not an impossible task. It takes some more work, but it's feasible.
Right.
Just real quick, I wanted to tie this back.
You got 20 seconds.
20 seconds, okay. We haven't really talked about the DC aspect of this. It ties back to the high penetration of solar. We actually are very excited about the potential for DC on low voltage power electronics, because it could potentially allow us to be that smart inverter and not actually keep customers from putting PV in, accelerate it, because they may not have to buy the inverter in the future. So it's very interesting to us, especially from the standpoint of we want to drive distributed energy resources into our service territories. We're not trying to keep them out. So this is the type of technology, with having the ability to get a DC bus out of it, that will allow us to do that.
See, if only Tesla had power electronics way back when,
I know.
they'd have actually already solved this.
And then on that, in 10 seconds, mandates over here, proper tools over here, and that's what we're working on, right? And so technology leading policy, right? Not policy leading technology.
Yeah.
So
I will say on your comment, that is probably the most, and it may not be something everybody thinks about, that would be the most transformational thing probably to hit this industry since we got rid of DC. Well, almost got rid of it. There's a few still out there.
It's coming back with a vengeance.
I'm still looking forward to, 100 milliamp USB ports. Get phones charged in less than 3 hours. So with that, we're actually quite a bit into question time. So we have about 10 minutes to go. I think we have a mic rolling around. So if you have questions, just kind of raise. And we got one in the back already. Eric, you have a loud voice if you just want to boom it.
It's definitely going to be a different economic approach, Eric. We are still in the evaluation process of where do we start? Because like I said, it's basically, you're going to just have to look at your complete feeder design again. So what you think you know about feeder design today, throw it out, start over, and really, where can we, because I mean, can we get away with smaller feeder lines, smaller services, smaller conductors? We're not even sure yet. And that does not even take into the account the upstream advantages that this type of technology can have beyond just a distribution feeder. And actually, the downstream inside potentially inside the home actually too. Because the other piece of this is it's a platform. You can do a lot of different things with it. So, but to your point about regulatory assets, I've said this a lot, and there's a couple of folks in this room that will yawn when they hear me say this. The utilities business model is changing. It's changing rapidly. We no longer can continue to get paid for putting capital assets in the ground and earning a rate of return on it until we depreciate it. The 30-year life assets are going by the wayside. These are 10 to 15, if we're lucky, 20-year devices. Comms is 5 to 7. How are we addressing this topic with our regulators so we can look at changing our business model? Because, and oh, by the way, if our business model has to change, our vendor's business model has to change too.
Got one all the way up in the front.
Thanks for that. You don't mind?
Okay. Thanks, guys. I can't pretend to have caught that. The earlier discussion being an economist, so you have to answer slowly for me here. But in Bala Power Networks, Graham Horn, we focus on the customer side using customer loads, networks of customer loads to help provide balance for the grid. So you touched on it there just a bit, Jason, at the end there, the role of the customer. And I'm just curious, it wasn't really the focus of the session, but what is the role of the customer? You talked a lot about safety and reliability and so on, but what can power electronics do for the customer experience? We had some discussion of that in one of the earlier sessions. Thanks.
specific to,
I mean, I had,
go ahead,
one of my previous companies was essentially doing power quality solutions for large industrial plants that required better power and, kind of immunity against voltage sags. But, that costs a lot of money. And, so yes, I think we can do a lot for the customers, but is that extra quality, extra reliability, is this something that they're looking for? And if they are, then they are probably paying a little bit more, for it.
I think to add, just within the scope of our conversation here, and we're in our talking about DC-based devices, one specifically, right? And we can go down a long list of customer value, customer benefits, but one specifically is the integration of DC-based devices. So something transformational is looking at the solar install and eliminating a $2,000 inverter and the maintenance 4 to 5 years, maybe 10 years if there's inverter manufacturers in the room, the maintenance associated with that inverter on the customer side, and moving that to a utility that may be better suited to manage that. So you're lowering your upfront install cost of a solar installation, and at the same time, you're avoiding the consumer maintenance issues that are inevitable with an inverter or capacitive, power electronics based inverter.
Think even bigger. Think about as a platform. If you have a hardened computer out in the field that you can download, I don't have my phone on me. Let me bring it up here. That you can download an app to potentially that tells the customer's having a voltage issue, and potentially you could talk to the meter on the side of the house from the transformer, the power electronics, and say, I need you to speed up your sample rate. I've saved me money by not having to send trucks out there, rolling trucks. I've also provided better customer service to that customer because I'm able to get them an answer instead of 3 to 7 days. I'm able to get an answer in probably 1 day now after just doing some evaluation without me actually having to roll anybody out there. So I'm looking at this more of a holistic platform of what can we do with power electronics in the field.
And some people groan when we start to throw out the telecom references, right? So half the room will groan, half the room will listen. And someone in a presentation at one point said, "Stop using the telecom references." But in looking at the infrastructure, certainly we saw the move of the access router push into the decentralized routers into our homes to help manage variability and to offer customization that Jason's referencing. So realistically, the last point of energy control today is the substation. So how can you offer customization services to 2,000 customers that sit downstream of that last point of energy control? You can't. So you need capabilities closer to the customer. These do it.
So we have time for maybe 2, maybe 3 questions. One right here. One in the back.
Anirudh from ABB. Thank you for the insight, especially Deepak and Naimish about the technical points. And one of the questions I had was, this is all customer-focused power generation, which is relatively new. So what are your opinions on the research which is invisible to the end user? And do you think that the efforts we are putting in the research right now, which potentially can affect the business model, are enough compared to the development of these renewable sources?
Well, I think. Go ahead. Well, you can go for it.
I was just going to say that, you mentioned the customer, but our customer is the utility. We love the consumer because I'm one of them, but we really don't do very much with the consumer. So only to the extent that they have PV or they have dynamic loads which are impacting the grid, that's where we come in. So at least from our business model perspective, we are completely utility focused and utility facing.
Yeah, no, I agree. I mean, look, I think it definitely relates to the first question over here, which is what is the benefit that accrues to the end customer? Well, it's simple. It's 2 things. It's what's the rate that they're paying and what's the level of reliability that they experience. Again, defining reliability broadly based on power quality and so on and so forth. These are operational technologies. So the impact of the grid is either, and hopefully, in terms of lower cost of operation of the grid on a recurring basis and lower capital investments as compared to the alternative going forward to support reliability of the system. It's that simple. So any research that goes on must, by definition, somehow accrue benefits to the operations of the utility system.
So we have time for maybe one very quick question.
See if this is quick or not. This is Andrew, and I'm from one of the vendors, Varentec, but I think I have an objective question just on economics. Assuming all power electronics is really becoming attractive to utilities, what are the major cost parameters that would make this transition from early stage to full adoption? Is this an individual customer by customer transformer, every transformer install, or is this a feeder level solution? What's the cost point that would help this be adopted?
Let me reframe that question. It's a good question, Andrew. So, again, it goes back to what is relevant here. And what's relevant is what's the total systemic cost. If I look at a single feeder from substation to all their loads, and I'm trying to solve problem X, maybe X is I want to do CVR, maybe Y is I want to make sure that I'm delivering voltage within the range if I'm on a highly penetrated PV system. Well, it's the total installed cost for the whole feeder that matters, right? sum up all of the investments you think you need to make, whether they're per transformer or every 10th transformer or every 20th transformer, and whatever that total cost is the one that matters. And so that systemic cost must drive the decision making here.
I'd like to add, I'm going to cut you off. You have 20 seconds.
20 seconds.
20 seconds, and I will actually cut you off this time.
One of the things that I think is important to look at here. I'm going to get cut off.
Yep, you are. You got 7. You
Just-
got
just-
7
just
seconds.
finishing up.
You're running out of it right now. 5.
The issue that really we need to address is not necessarily the cost of silicon carbide or gallium nitride or any of the technologies you're alluding to. If the consumers continue to adopt technology the way they're adopting at this stage, and I'm specifically pointing to photovoltaic and the businesses that are empowering them to adopt these types of technologies, the utilities will figure out a way to solve those problems. And so it's not necessarily a price point that needs to be met in terms of cost of manufacturing. It's that the consumers need to continue to adopt certain technology that's going to require advanced technology on the grid.
See, now you got me in trouble going over. So with that, I want to definitely say thank you to our panelists, and hopefully a little. If you've ever had the opportunity to talk to any of these guys, they will go on for quite some time. So if you have additional questions, please approach them. I've found, outside of Jason, who got more than he bargained for today, that all of these guys are happy to talk throughout the conference. So with that, I think we're transitioning directly into the smart inverters panel. So my colleague MJ will be switching on, and just stick around.